Today we'll be talking about gravity and specifically how Newton came up with a theory of gravity that would apply to both the physics of things moving on the Earth and also things moving out in space. So we'll be talking about Newtonian gravity, and this is a view of the Earth from the surface of the moon, which is the only place humans have been outside of the Earth. Last time we talked about conservation laws. We covered conservation of momentum, which dealt with collisions, conservation of angular momentum, which it turns out is what keeps planets spinning on their axes and orbiting the sun. And we talked about conservation of energy, where you don't create energy, you just transfer it from one form to another. So, which of the following of these quantities is conserved during a car accident? And there can be multiple correct answers. Yeah, so the total energy will always be conserved. In a collision, momentum is conserved. In this particular collision, the kinetic energy got transferred into the energy of destroying the car and the building, so that didn't get conserved. And then forces are not a conserved quantity. Okay, so we did talk about gravity a little bit when we were talking about kinematics and how things move, but we're going to go a little bit more in depth with gravity, talk about how we determine the strength of gravity, then we'll talk about Newton's theory of gravity and how that applies to Kepler's law and modifies them in certain ways. Then we'll talk about the energy that comes from gravity and how that applies to orbits, and then we'll talk about tidal forces and how gravity causes those. Okay, so here is a graphic to explain how gravitational attraction works. So anything that has mass will exert some gravity and feel a gravitational pull. So we have two masses, m1 and m2, and they're separated from each other by some distance r. The force of gravity that these objects feel is the product of their masses, so multiply m1 and m2, divide that by the distance between them squared, and then multiplied by this constant capital G. So very important to note, capital G is different than lowercase g. So a couple of lectures ago, we talked about lowercase g, and that was 9.8 meters per second squared. Capital G is not that. So anytime you see capital G, it's a different value. We'll talk about what that value is in a second. So every mass will experience this attraction to any other mass. The bigger you make the masses, the stronger the gravitational attraction is, and the farther away you separate the masses, the weaker the gravitational attraction is. And this is true for anything that has mass. And remember, mass is just an object being made out of stuff like atoms. So people have masses, planets have masses, stars have masses. And so all those things will be gravitationally attracted to each other. Okay, so I've told you that near the surface of the Earth, the force of gravity is mass times little g. And now I'm introducing a new formulation for gravity that is this capital G times mass 1 times mass 2 divided by r squared. So anytime you're introduced to a new equation, you should check that it's consistent with what you already know. So let's do that. So this capital G gravity we'll call Newtonian gravity. And lowercase g will just be surface gravity. So we have this equation. And this equation. Maybe I'll write it how I have it on the board, and then I'll plug in some values. So this capital G is this 6.77 times 10 to the minus 11, and it has some weird units that just allow it to cancel these other units out and leave you with a unit of force. So the picture that we're really looking at is, let's say I'm a person standing on the surface of the Earth. I've told you that the force of gravity I feel from the Earth should just be my mass times 9.8 meters per second squared. And now I'm telling you that your mass should also, or your force of gravity should also be equal to this mass of the Earth times your mass divided by the radius of the Earth squared. So let's plug in those values for G, mass of the Earth, and then your mass, let's say you weigh 100 kilograms, and then the radius of the Earth, 6.37 times 10 to the 6 meters. And then we have to square that. And that's supposed to equal 100 times 9.8. So if you look on both sides, there's 100, so the mass of the person is not going to matter. And if you plug 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 and divide that by 6.37 times 10 to the 6 squared, what you'll get is everything on the left side is equal to 9.8, and then that just equals G. So these things are where you can derive the value of lowercase g from. So for any object, if we wanted to do this for the moon, so the moon has a different radius and a different mass, we could plug it into this kind of formula. And calculate the gravitational acceleration of the moon if you were standing on the surface of the moon. Or we can do it for Mars or Venus or whatever we want. So what we wanted to see here was that these two equations are in fact equal to each other at the specific point where the person is standing on the surface of the Earth. So this new formula that Newton came up with is consistent with what you experience in everyday life, that you, standing on the surface of the Earth, you just have some constant gravitational acceleration. But this new formula, where you have two masses separated by some distance r, is going to apply to things in outer space, whereas the original mass times acceleration due to gravity doesn't work in space. So how does this new formulation of gravity apply to and change Kepler's laws? So the first law that Kepler came up with was that your orbits around the sun are either circular or, in the case of the planets going around the sun, were elliptical orbits. Newton extends that to apply to all of the conic sections. So remember, we talked about how if you slice a cone in different angles, you can get these different kinds of curves. So you can get a circle, you can get an elliptical orbit, and those are bound orbits, so the object would keep going around that star. Or you can get these unbound orbits that are parabolic or hyperbolic, where, let's say it's an asteroid from a different solar system or something like that, where you come close to the star, but you basically have too much kinetic energy to stay in a bound orbit, and you get kicked back out of the solar system. So that was the first way that Newton modified Kepler's laws, now that he had a better theoretical framework to work from. The next modification that he made was to Kepler's third law. So Kepler's third law dealt with the period of a planet going around the sun, and it's related to the distance away from the sun. I'll write down that equation on the board that Kepler came up with, and then we'll compare it to the new equation that Newton came up with. So this was Kepler's third law. Was just p squared equals a cubed, where p is the period or time in years, and a was the distance in astronomical units. The big caveat to this formula is this only applies to objects orbiting the sun and the formula that Newton came up with will apply to any object orbiting any other object. So if we want to talk about the moon orbiting the Earth, or one of Jupiter's moons orbiting Jupiter, then we can use the new version of Kepler's laws that Newton came up with. So if you encounter a problem where they're asking about something going around the sun, then this is probably the easier formula to use. But if you're asked about something orbiting any other body, then you'll have to use this new equation. And so this new equation actually reduces down to Kepler's original law. If we take a look at the Newton version, we've got the p squared, so that's the same. now we have a 4 pi squared in the numerator, we have a g, we have an m1 plus m2 in the denominator, and then we have the a cubed again. So it turns out the mass of the sun is much bigger than the mass of anything else in the solar system. So basically, the mass of the sun, say, is 1 trillion, and the mass of any of the planets is 1. If I add 1 to 1 trillion, I'm not really changing the value of the denominator. So adding a really small mass to a really big number doesn't change the value. So it turns out you can kind of just ignore the really small mass, and when you do that, you take 4 pi squared divided by g times the mass of the sun, and this all basically reduces down to a value of 1. And so if you choose your units correctly, in the limit where m1 is the sun and m2 is anything else in the solar system, you get back the original Kepler's third law. But this is more powerful in that it can extend to any other masses. So when we're talking about the mass of the Earth and the mass of the Moon, now we can use this equation to get an accurate calculation for, say, the period of the Moon, or the orbital distance from between the Earth and the Moon. So this is very important to be able to extend Kepler's third law to objects that are not just orbiting the sun. So let's do an example of where this might be important. So one of the ways that we can use this is to actually calculate the masses of objects out in space. So let's say we want to measure the mass of Jupiter. How would we do that? We can't put Jupiter on a balance beam and add a bunch of masses and see how it balances out. So how do we actually know what the mass of Jupiter is? Well, we can do some observations and plug the data into this equation and use that to calculate the mass of Jupiter. So in this equation, let's say m1 is the mass of Jupiter, and that's what we're trying to calculate. M2 would be the mass of one of Jupiter's moons. G is this constant. So what we would do is we would need to measure the period of the moon's orbit. So let's say the period that we measure is, let's say it's 10 days. Then if we know the distance to Jupiter, we can use the angular separation distance between Jupiter and its moon to calculate the distance between Jupiter and its moon. And let's say we have that number, and it'll be I don't know, maybe 10 to the 7 meters. Now we'll do the same trick we talked about when we were talking about the sun. Jupiter is going to be much more massive than any of its moons. So when I do m1 plus m2, that's basically just the same as the mass of Jupiter. So now our equation look something like this. And now it's just algebra to isolate M1, which is the mass of Jupiter. So M1, we would multiply that to the other side and then divide the p squared over. So you would get 4 pi squared a cubed over g times p squared. And then all of these numbers that we measured, like the period of the moon's orbit and the distance between Jupiter and its moon, plug that into here, make sure you convert your units correctly, and we can use that to calculate the mass of Jupiter. So anytime you're seeing a mass of, say, a planet or a star, when we start learning about stars and other solar systems, this is the procedure, or one of the procedures that we do that allows us to calculate the mass of that object. So basically any mass you see from now through the rest of the semester will be calculated using this modified version of Kepler's third law. So it's very powerful for measuring the masses of objects in space. Here we go. So this was the this is the formula for potential energy due to gravity. So just like there was a modification that Newton had to make for the force of gravity, there's also an equivalent modification for potential energy due to gravity. So when we were talking about lowercase g gravity, we said if you increase the height something is off the ground, you increase its potential energy. There's going to be a similar relationship here, where now if we increase the separation distance between two objects, we're similarly going to increase the potential energy. And that's why this minus sign out in front is very important. So this equation looks a lot like the force of gravity equation. The only differences are the r is not squared in the denominator, and there's this negative sign out in front. The negative sign out in front is what turns this into it's what makes the potential energy increase when I move the objects further apart. If there was no minus sign in front, if I increase my radius r, I'm making the number in the denominator bigger, which means I'm making the fraction smaller. But if I put the negative sign out in front, a smaller negative number is actually bigger than a larger negative number. So this negative sign allows my concept of potential energy due to gravity to still work. And if you take calculus, then this negative sign is also a consequence of calculus. So when something is orbiting an object like a planet orbiting the sun, it has a total amount of energy. It has some gravitational potential energy, which we just saw the formula for, and it has some kinetic energy. And the total amount of energy doesn't change, and it just kind of switches between gravitational potential energy and kinetic energy. So when I'm at this point on the left side of the orbit, farther away from the sun, my potential energy due to gravity is bigger because I'm farther away, and so my kinetic energy goes down, so I'm moving slower. Then as I get closer to the sun, my gravitational potential energy is getting smaller, and it's getting converted into kinetic energy. So it's the same kind of logic when we are talking about forces, but it also applies to energy. And we'll see some examples in a moment of why it can be more useful to think about energy and the consequences for how we can calculate some very interesting quantities using energy. So as Earth orbits the sun, the force of gravity the sun exerts on the Earth is the same as the force that Earth exerts on the sun. Is that true or false? Yeah, so this is another Newton's third law concept. So even though the sun is bigger than the Earth and the Earth is orbiting the sun, the force that they feel is the same. And the other way that you can see that is by looking at the equation for the force of gravity. So force of gravity, G m sun, m Earth, over r, which will just be the distance between the sun and the Earth squared. So because the mass of the sun and the mass of the Earth are both getting plugged into the equation, they're both going to be feeling the same force. So both masses get plugged in, so both objects feel the same value of this force. Or you can just say Newton's third law says there's always an equal and opposite reaction force. So now we're still talking about orbits. So we on the Earth are orbiting the sun, but we like to launch things off of the Earth and explore outer space. So how can we actually launch something and leave the Earth and have it orbit another object or orbit the sun in a different way than the Earth is orbiting? So there's a couple different ways that you can do that. One way is through friction or atmospheric drag. We'll come back to that when we talk about the moon in a little bit. And another way you can change the orbit that you are on is through a gravitational encounter. So this blue line is the orbit of a comet. The orange line is the orbit of Jupiter. The dotted line is the orbit before the comet interacted with Jupiter. So it would have just kept going in this really big orbit around the sun, but it got a little too close to Jupiter, so Jupiter's gravity caused it to basically deflect its orbit a little bit, and now it orbits the sun in a much tighter orbit than it previously did. So the solar system is filled with several objects that have their own gravitational forces, and so it can be really complicated to predict these kinds of orbits because there's a lot of moving pieces. But just getting too close to another object that has mass can change your original orbit. And when we talk about launching satellites later in the semester, we'll add another way that we can change our orbits when we talk about like rocket thrusting and that kind of stuff. Okay, so this is one of the consequences or one of the applications that we can use from thinking about conservation of energy. How fast do we need to launch something from the Earth so that it will leave Earth's orbit and we can go explore Mars or maybe another solar system? So that concept is called escape velocity. Depending on the speed at which I launch something off of the Earth, I can either get stuck in a bound orbit around the Earth, whether that's a circular orbit or an elliptical orbit, or if I can impart a really high escape velocity, then I can leave the orbit of the Earth and not be in a bound orbit anymore. It turns out that value is about 11,000 meters per second or 25,000 miles per hour. So if you're launching a rocket and you're trying to get to Mars, you need at least this much energy to break free from the Earth's orbit. So where do we get that number from? So you are not going to be asked to do this derivation, but this final answer is one of the equations on your equation sheet, and so you'll need to know how to plug numbers into it at least. So to derive the escape velocity, we just start with our conservation of energy statement. Whatever energy we start with has to be the same amount of energy that we end with. So we could start with some kinetic energy and some potential energy, and we could end up with some final kinetic energy and some final potential energy. Our rocket ship is going to start on the surface of the Earth, and we're going to launch it with some initial velocity. So it's going to have initial kinetic energy and initial potential energy. The concept for escape velocity is what is the minimum velocity I need to escape the Earth. So my final picture is basically I've gotten far enough away from the Earth that I'm no longer feeling any potential energy due to gravity from the Earth, and I've used up all of my kinetic energy so that I have none left. So that's why the right side is 0, is because we're basically finding the minimum escape velocity. Kinetic energy is 1/2 mv squared. I'm using the 2 subscript to denote the mass of like your rocket ship, and the 1 subscript is for the mass of the Earth. So we have the kinetic energy of your rocket, and then the potential energy due to the rocket sitting on the surface of the Earth when you launch it. I'm going to move the potential energy to the other side, and now it becomes positive. Then there's an M2 on both sides, so those can cancel out. So it turns out the mass of your rocket doesn't matter. Now I'm left with 1/2 velocity squared and gm1 over r. Solving for the initial velocity, we get square root 2 times g times the mass of the Earth divided by r, which is the radius of the Earth. And so this is the escape velocity. Any velocity greater than that number, and you will comfortably leave Earth's orbit. Any velocity less than that, and you would be stuck orbiting the Earth once you got off the surface. Or you might not even make it to orbit. So when you plug in the value for g, the mass of the Earth, the radius of the Earth, you'll get that about 11,000 meters per second that we had on the previous slide. So something interesting that we can do using this formula as a starting point is think about some velocities that have special meaning in physics. For example, what's the fastest that anything can travel in the universe? Speed of light. So what happens if we set the escape velocity in this equation to be the speed of light? Anyone have any guesses? Okay, well, let's see. What happens if the speed of light is the escape velocity? So take our equation for escape velocity, replace escape velocity with c, which is the speed of light, do some algebra to rearrange this, and we derive a radius that equals 2 times g times the mass of the object divided by c squared. So it turns out this radius is the radius of a black hole. So just using some introductory physics and this idea of setting the escape velocity to be the speed of light, we just derived the radius of a black hole. So a black hole's definition is something that is massive enough and dense enough that nothing can escape it. Nothing can move faster than the speed of light, so if we set that as our escape velocity, nothing can leave this gravitational pull of this object, and the radius at which you can no longer escape is this radius r. So using this concept of escape velocity and the speed of light, we just derived what's called the Schwarzschild radius of a black hole. So we'll have a whole lecture later on in the semester about black holes. This particular radius that we just derived is for a non-rotating, neutrally charged black hole, which of course implies that there are black holes that rotate and have electric charges. But this is kind of the most basic black hole you can think of. And it turns out if you take higher level physics where you're doing general relativity, when you derive the radius of a black hole, it all simplifies down to this answer. So just using some Newtonian physics, you were able to do some pretty cool things like learning about black holes. And Schwarzschild is just the name of the person who originally did this calculation. So he gets a formula named after him. The last thing that we'll talk about in regards to Newton's formulation of gravity are tidal forces. So tidal forces are a consequence of the objects that are experiencing the force of gravity are not point objects. They have some extended size to them, like a planet or a moon. So if I look at these two objects, let's say the object on the right is the one exerting the force of gravity that we're interested in. And so the closer side to that small object on the big object is going to be experiencing a greater gravitational force than the far side of the large object, right? Just because it's closer to the object that's exerting a gravitational force. If you want to calculate what that tidal force is, or the amount of force that's basically causing the object to stretch, it looks almost the same as the regular gravitational force, but we have to include d, which is the diameter of the object experiencing the tidal force, and then instead of r squared in the denominator, it's r cubed. So an object with a bigger diameter is going to experience a larger tidal force, and because this is r cubed in the denominator, the tidal force will reduce very quickly the farther you get away from an object. So this tidal force is what's responsible to what we call tides in the ocean. So why do we experience tides on Earth is because we have a moon that's orbiting us and is fairly big. So this near side of the Earth is experiencing more force than the far side of the Earth. That causes a force in the horizontal direction pointed towards the moon. And so the Earth is kind of stretched in this direction, and water is not a solid material, it's a liquid, so it can change its shape. And so along this axis pointed towards the moon, you can get a high tide, and you can get lower tides on the opposite axis. But it's not just the moon that causes tidal forces on the Earth, but the sun also exerts tidal forces on the Earth. And so this results in what are called spring tides, when the sun and the moon are in alignment, causing the greatest amount of stretch for the Earth that it feels from the tidal forces. Or neap tides, which is when Earth experiences the minimal amount of tidal forces, because the tidal forces of the sun and the moon are perpendicular to each other, and they don't quite cancel out, but it's much weaker effect. So the spring tides will occur during new moon and full moon, because that's when the sun, moon, and Earth are all in alignment. And neap tides, which are the weaker tides, will occur first quarter moon and third quarter moon, where the sun, Earth, and moon are not in alignment. And so here's a video of one of the most extreme tides that is experienced on the Earth. So you can see in this little bay, I think in Canada, how high the water rises during high tide, and then how low it gets during low tide. And that's all a consequence of the moon orbiting the Earth, and also the sun orbiting, or the Earth orbiting the sun. Oops. There's this idea of tidal friction. So the fact that we have a moon orbiting us is actually causing the Earth's rotation to slow down a little bit, and it's causing the moon to sort of drift a little bit away from the Earth over time. There will be a better diagram on the next slide of that. And a consequence of this friction is that the moon is now tidally locked to the Earth. That tidal lock means that the moon, the part of the moon that's facing the Earth is always the same. So we saw that in lab when we talked about how long it takes for the moon to rotate. And this idea of tidally locking is due to these tidal forces. When we talk about exoplanets in a few weeks, there will be a special class of exoplanets that are tidally locked to their star, and that has some interesting implications for, can life survive on planets that are tidally locked to their stars, and what would that look like? So here's a good diagram for what the tidal friction is. So we have to remember everything is always in motion. So this is a still picture, but the Earth is spinning on its axis, and the moon is also orbiting the Earth. So if everything was stopped, this point that's closest to the moon is currently experiencing the most tidal force, or the most force, and so there's a tidal force that's pointed towards the moon. However, the Earth is rotating, so that part that was experiencing the most force is now no longer pointed towards the moon. Now it's kind of pointed a little bit away from the moon. That tidal force caused a bulge in the Earth, and so now there's a little bit more mass kind of off-center from the moon, and this is causing the Earth's rotation to slow down, because now the point that's a little bit stretched out is getting a force pointed back towards the moon, which is in the opposite direction that it's trying to rotate. And so you get this kind of slowing effect over time. And remember, all of these tidal forces that the Earth is experiencing, the moon is also experiencing tidal forces from the Earth. Okay, so we saw Newton's new formulation of gravity, where you multiply the masses together and you divide by the separation distance squared. We saw how that new formulation of gravity changes Kepler's laws. We can also think about, we saw Newtonian gravity as a force. We also saw Newtonian gravity as energy, and we saw how we can use that energy to talk about escape velocities. And we use the escape velocity to derive the radius of a black hole. And this force of gravity is also responsible for tides. And I'll leave you with this kind of summary of the different formulas that we learned. So potential energy goes as 1 over r, force of gravity goes as 1 over r squared, and the tidal force goes as 1 over r cubed.